Hello friends, welcome to this video on material strength levels. So you may wonder whether material has different levels of strength because generally we understand any material will have its own single strength. But it is not so because when we have a material and want to declare its strength, we have to make a lot of tests on the material, and test result will have their average value, standard deviation, dispersion and so on, and we have to select which one should be declared as the strength of the material. On the right hand slide you can see a building which has got damaged due to earthquake. So question arises, during the damage what strength the building was exhibiting? This is an important question. So all these aspects we want to see in this video. So because you test the material and you get so many results, maybe 10,000 results, and out of that you want to arrive at a definition of the strength of that material, you have the probability coming into picture. So if you have a normal distribution of the values, that is the values are equally distributed about the mean, then it is called a normal distribution. In that case, a probability density function is a parameter which will be defining your probability. So it is given by this expression where x is the parameter value, different parameter values, and mu is the mean, and sigma is the standard deviation. You can plot it with the PDF in the vertical axis and probability of accidents in the horizontal axis, and you get a symmetrical curve if it was a normal distribution. If you take the middle line, then corresponding to this line, whatever strength is there, that is called the mean strength. You have to remember that in the probability curve there is no strength value here available. So it is only showing different levels, different probability of accidents of this strength. So if it is 50% probability of accident, that is 50% results will be higher and 50% results will be lower on the left hand side, then that strength will be called as the mean strength. The distances from the mean will be given in terms of sigma. So 1 sigma, 1.64 sigma, etc. on the left or on the right. The total area of the probability curve is 100% or 1.0. So this is 50% line. Now let us take another definition of the material. So how do you define it? When you invent a new material, you carry out a lot of tests, tensile test or compression test, study the results and arrive at a probabilistic definition which is called as characteristic strength of the material. So it is the strength level below which not more than 5% results fall. Let it be symbolized by K for characteristic. So you have the mean value of the strength around this line, level of mean value of the strength around this line, which is probability of accidents 50%. If you go on the left hand side, you are going to lower and lower strengths. If you go by a distance of 1.64 sigma, where sigma is the standard deviation of the test results, then you arrive at this line where the materials having strength lower than that value here at that blue line will be only 5%. Let us further understand. This blue line is corresponding to a strength level which has 95% chance of accidents on the right hand side and 5% chance on the left hand side. So it indicates the 95% results are higher than this level of strength corresponding to the blue line, and 5% results are lower. This line corresponding to the strength of this line is called the characteristic strength. So it is recognized by looking at the mean value and the standard deviation distance of 1.64 sigma towards left, then you get the blue line. So characteristic strength will indicate a strength where 5% of the results may be falling below this value of the result, below of the characteristic strength. Now the next strength level is the expected strength or the mean strength. It is the strength level below which not more than 50% of the results fall. So we express this by F expected. So it is shown here 50% of the results are lower than this value. The strength level corresponding to the mean line is the mean strength, and 50% results will be lower than this, and 50% results will be higher than this. So this has the most likelihood of occurrence, mean strength. That's why it is called most expected value. Now let us see another definition, which is the extreme strength. So it is the strength above which not more than 5% of the results will lie. This is symbolized by F, extreme. So again we take the mean line by the red vertical line here, and we go at a distance of 1.64 sigma towards right. So we reach at 95% probability of exceedance level, and only on the 5% area lies on the right hand side. So strength that corresponds to this blue line is the extreme strength, where only 5% of the results are higher than this. So it is a very high value of the strength, very high value of the strength, beyond which only 5% results are falling. Any material definition starts with a characteristic. So it is here where 5% results are lower. So the extreme strength definition has to be given in terms of the characteristic strength. So characteristic strength is 1.64 sigma from the mean, and extreme strength is another 1.64 sigma towards right. So total distance from the characteristic strength is 2 multiplied by 1.64 sigma after the extreme strength. Now we come to the limit strength, which is very popular term because we use this in RC design as well as in steel design, and limit state design is the present day's popular design. It is characteristic strength divided by a partial safety factor for the material. So let us write it by F limit. So you have the probability curve, the mean value is at the middle, and the characteristic value is at the 5% level at the blue line, and the limit strength is still divided by partial safety factor, so it goes still towards the lower side. So exactly we are not defining how many percentage is lying below the limit strength. If you read the probability theory, you can find it out based on the partial safety factor, how much lower, how much on the left hand side you have gone to, and what is the result lying lower than this. So it is taken lower than characteristic so that only fewer samples of your building etc. or structure will fail, and most of the buildings will be surviving, lying on the right hand side of the red line. So limit strength is given by F limit equal to Fk by gamma m. Gamma m is the partial safety factor for material, and Fk is the characteristic strength. So for concrete it is Fk plus 1.64 sigma. For concrete Fck will come, we will see in the next slide. For any material, whether it is concrete or steel, this formula will hold good. Expected strength equal to characteristic strength plus 1.64 sigma. Extreme strength equal to characteristic strength plus 2 multiplied by 1.64 sigma for the material. So with this we can have this tabulation, strength levels and for concrete and for river. The characteristic strength for concrete is Fck, for steel it is Fy. Limit strength is characteristic divided by partial safety factor. For concrete it is gamma mc. Gamma mc value is 1.5 in Indian code, and for steel Fy by gamma ms value for Indian code is 1.15. If you take reciprocal of 1.15, you get 0.87, which we shall see coming in the formula in the next slides. Expected strength equal to characteristic strength plus 1.64 sigma c for concrete, and Fy plus 1.64 sigma s for river. Sigma s is the standard deviation for steel, which is generally taken as 50 megapascal. Extreme strength Fck plus 2 times 1.64 sigma c for concrete, and Fy plus 2 multiplied by 1.64 sigma s for river. Now limit strength, let us revisit again because it is so popular in the RC design. This stress block is known to all the Indian readers. In American code it is rectangular stress block, in Indian code it is rectangular parabolic. So it is maximum strain at the top of the concrete is allowable is 0.0035. from strain 0.002 and lower side, the stress block is parabolic, and above 0.002 it is rectangular. Now you see here at the top curve here, the value is FCK, so this curve corresponds to the characteristic strength. And 0.67 FCK is coming, or 2/3 of FCK is coming because of the Platon effect and the size effect in the cube tested in the laboratory. In the laboratory in India, the strength of concrete is given by the 28 days compressive strength of 150 mm cube. So this size is much smaller than the sizes that will be encountered in the field. So this is called the size effect. Lower size will give you higher strength. And due to the fact that the cube is put under the two steel platens and tested, it shows more strength than actual. So this tested strength FCK is reduced by 2/3, and this is, you can say, available strength for the cubes. And this is to be divided by partial safety factor for concrete to get the limit strength. So limit strength is this 0.67 FCK divided by 1.5 for Indian code. So this area is the limit strength parabolic rectangular diagram. So compression strength, compressive force exerted by this stress block is the compression force available in the concrete. So let us see the expression for this. Expression for this is available in the IS code. It is equal to 0.33 FCK B into X. X is the depth of neutral axis and B is the width of the beam. So 0.36 is coming out of this 0.67 FCK divided by 1.5 together. So this is limit compression strength in limit strength. In characteristic level, the compression strength given by compressive force given by concrete is 1.5 times, removing the partial safety factor as here. So 1.5, 0.33 FCK Bx. For expected strength, it is 1.5, then 0.36 is there coming from the formula, and the FCK is changing to FCK plus 1.64 sigma c and multiplied by Bx. The extreme compressive force arising out of concrete is 1.5 times 0.36 within parenthesis FCK plus 2 multiplied by 1.64 sigma c multiplied by Bx. So depending on the strength level you want, the moment of resistance of the section you want, whether limiting moment of resistance or characteristic moment of resistance or expected moment of resistance or extreme moment of resistance, you will be using this formula to get the compressive force in the compression stress block. The standard deviation sigma c is given in IS code. Similarly, it is given in other codes also. M stands for mix, and these values give you the characteristic strength at 28 days cube testing. M10 and M15 are not structural concretes. These are used for, say, foundation laying, etc. M20 onwards, these are used in structures. So 20 and 25, the standard deviation is 4 megapascal, and 30 and up to 50 it is 5 megapascal. Limit strength of steel. Nowadays, high strength deformed bars are used, which do not show any specific yield point, and the stress strain curve is like this, usually nonlinear. So what is the corresponding stress and strain you can get from the codal diagram or also in the SP16 in Indian publication. So the limiting tension available in the concrete in the steel will be given by 0.87 Fy AST. Characteristic tension force from the river is FYST, removing the partial safety factor. Expected value Fy plus 1.64 sigma AS multiplied by AST. And extreme strength, extreme tensile force out of the river, tension river is Fy plus 2.1 multiplied by 1.64 sigma S multiplied by AST. Sigma S typically is 50 megapascal, though it is not given in the code. Now moment of resistance of the sections you want. and you may want it at the limit strength level, characteristic strength level, or some other level of your interest. So how to get it? Let us see. In the beginning, assume a neutral axis depth say x, and assume that the strain at the extreme fiber of the concrete is 0.0035. For this condition, find the compression force in the concrete, say Cc. So here is the strain diagram. At the top, the strain is 0.0035, and at the bottom it is epsilon st. At the compression steel level, the strain is epsilon cs. Now, based on the amount of strain here, this epsilon cs or epsilon st, the compression force in the compression steel or tension steel will be found out corresponding to their stresses FCS and FST. So find the strain in tension steel and compression steel, that is the what is the value here and what is the value here of the force. Find tension steel T and compression steel CS. From the strain you have to find these values. From the strain, first the stress, then stress multiplied by area will give you the total tensile force or total compressive force in the compression steel. Find total compression now out of the compressive force in the concrete and compressive force in the compression steel, and check if C is approximately equal to T or not. If they are approximately equal, then value x is correct. Value x chosen is correct. If not, you select another value of x and go to step 2 again. Now whether x is to be increased or decreased, you can decide. If you increase the value of x, then epsilon st will be reduced, t will be reduced. If you reduce the value of x, epsilon st will increase and t will increase. So accordingly, seeing whether t is much larger than c or not, you can decide whether x to be increased or decreased. And when it is c equal to t, you can stop, and the moment of resistance equal to c into lever arm or t into lever arm. That you know from your knowledge of RC design. Now question is, why do we require the strength levels? Let us see. For material strength definition, we require the strength definition is the characteristic strength of the material. For design purpose, we require limit strength. For nonlinear analysis, expected strength is required. In the first slide, I asked the question, which strength the building will be exhibiting during earthquake? The answer is, nature does not know your all theories, whether limit strength design or some other strength design. It will be finding the easiest method. So it is the mean strength, which is highest likelihood of occurrence. So during damage, your materials will be exhibiting expected strength or mean strength. So that knowledge is required about the mean strength. For capacity design, extreme strength is required. Capacity design we shall be highlighting in some other new video. Extreme strength will be required. We will see that there will be ductile link and brittle link. Extreme strength of one link should not be more than the limit strength of the other link, so that only ductile failure is there and not brittle failure. The numerical details for the calculation of moment of resistance or limit state level, expected level, etc., you can refer to my book, Performance-Based Seismic Design of Structures, going to be published soon by CRC Press, Tellerson Francis. It is expected to be published within December this year. So I wish to see you as my reader of this book in future. Thank you. Thank you very much for watching. Please subscribe the channel, like and share the video, and give your inquiries in the comment box. I shall be glad to answer your queries to the best of my knowledge. Thank you, and see you again in the next video.